Okay, good morning, everyone. I think we can start. Welcome back. I hope the dinner was nice. And yeah, very happy to go to the last day today. And we are happy to announce that all the 5 groups sent their presentations on time by 8:59. We had all of them. Very good, well done. So the first target is achieved. Perfect. And we are looking very much forward to the presentations and discussions after lunch. But first, we're going to have 2 lectures of really eminent, prominent scholars in the field. So we're very happy they made time in their busy schedules. And we start by a talk by Riahi from IASA. We just had this rule to give a brief 1-2 minute introduction about yourself, how you got into IEMs, your kind of career pathway or something you want to share also on a more personal level, and then go into the speech. Thanks.
Okay, thank you, Johannes. Yeah, it's a real pleasure to be here and to join you for this last day. Yeah, about my person. By training I'm an engineer, so I've been constructing power plants before I came into the integrated assessment field. Now I'm leading at IASA the so-called Energy, Climate and Environment program. You can hear that there's energy is part of it, because energy is also my background there. I would say that I was a PhD in economics, so that helped a lot to have basically an engineering background, but to speak also the language of the economists. But if you are once an engineer, you will always remain an engineer. So I would see myself more as an integrated assessment modeler with an engineering background. And have worked also with the IPCC since quite some time. And recently have been also involved in some of the policy processes. So I'm part of the advisory group of the European Union on climate change. Actually, I will bring that a little bit into the lecture. So what I would like to present today is complementary to what you have heard so far, give you a little bit of an basically historical perspective. So how did we get to the energy system that we have today? Then talk a little bit about demand side transformations. What is the advantage of those? How can we accelerate transformation through a service-oriented system perspective? And then talk about things that are very much in the public discourse, but can be also studied scientifically in a rigorous and systematic way. It's about feasibility and fairness. So to which extent are the transformations that we find in the literature feasible, and what perspectives on fairness exist? But let us start perhaps from the historical perspective. I think it's really important if we, when we look 100 years into the future, to also look back perhaps 100 years or more, and think about, okay, what were the main transitions that were happening, which have been shaping the energy system, but how has also the energy system basically shaped societal and technological economic transitions of the past. And I would say the main changes that we could observe in the past are, at the one hand, interestingly, we moved from a mainly non-commercial biomass-driven energy system to one which is commercial and driven by fossil fuels. So we have a transition from renewables to fossil. We have a transition from a society that in the pre-industrial era was primarily agricultural, from a rural society to a predominantly urban one, enabled by fossil fuels, by energy densities of fossil fuels, which allow also very dense energy demand centers as the industries and as well as our cities. Economic activity started out originally in the south and during the Industrial Revolution, and partly because of the advantage of the early energy system that emerged, moved to the north, where industrialization took place first, and is moving now again more into the direction of south. So we have also a movement between where is the economic center of the world. we have moved from always more convenient and more flexible types of fuels. Yeah, although it's the cheapest way to heat your home with coal, nobody would go into the cellar and shovel coal into an oven, right? So you want to have a button somewhere, you click it on, and it's warm at home. And this has also shaped our energy system. We have improved efficiency and productivity. Our system has become more and more complex because of many conversion stages. You call that in the literature conversion deepening, electrification. And we have increasing supply and demand densities because of the urbanization. And we have also seen massive desulfurization. Some problems got solved. Actually, we have also seen massive decarbonization in the past. So most of the emissions in the past were actually not emitted, but these autonomous trends have been too slow. So our system grew faster than the autonomous improvements within the system, and that's why emissions have generally been increasing. Okay, so if you look at the energy system of the past, long-term perspective, the last 150 years, basically we saw major substitution, but also basically, first of all, energy system, of course, grew massively. We have new energy carriers in the system. Now, these are the traditional ones, but from the perspective of 1850, there was a succession of different innovations that basically drew the fossil energy carriers into the market, starting, of course, with the steam engine at the beginning of the 19th century, then electrification. We have the gasoline engine at the beginning of the 20th century. And then the emergence of more and more electrical appliances, which basically made the substitution from biomass to coal, to oil, to gas, and led to the dominance of the fossil fuels nowadays. So this was an innovation-driven and demand-driven change. And as I mentioned earlier, this change, of course, over the same period of time also enabled the massive urbanization that we have seen. So 1850, a society which, from the population perspective, this is roughly today. And not only that population grew, but most of the population growth in the future is expected to be in the urban areas. And in the past, we have seen that basically the fraction of population living in the urban areas to increase. And if you look into different scenarios, actually the difference among the scenarios in terms of what they project, how much urban population we have on the planet, is relatively small. So it's a very, very likely future that we have further increasing urban population. And since a few years, there are more people living in cities than in the rural areas in the world. Yeah, another, I think, important aspect to keep in mind is historically, and now I'm showing a graph where basically on this axis you see income, affluence, increasing affluence, and on this axis we see primary energy use over time. And with increasing affluence, we had, of course, increasing energy use. I think that's in the mind of everybody, but we had a very past-dependent evolution of energy use in the past. If you look at similar development stages here approximated to income, for example, at $10,000 per capita, we see that countries which traditionally are resource poor, good examples, Japan, France, and Austria, for example, developed on a much more efficient less energy intensive path compared to regions and countries which traditionally are very resource rich. And this is particularly the US, which at similar per capita income always had around double the energy use than, for example, many of the European countries, which is an indication also of that if you have more resources, you also are more wasteful in the consumption of those resources. Generally, this trend has been an increasing trend, particularly England and the UK flattened at some point, where basically the dominance of coal in the system became smaller. Coal has been abundant in the UK, but fossil fuels are not. And I think you can see also interesting other events here. For example, anybody an idea what this could be? This very strange, bumpy thing. So you can see also here the time, right? So this is the GDP axis. Different dots here give you different times. Basically, we start in 1800 and then we go up to this one is basically the First World War, and what was following is the financial crisis, or the Big Depression of the 1920s, and this is the Second World War. As you can see, basically in this affluence energy curve, even world wars are just short bumps, and then it continued more or less along the quite path dependence evolution. Yeah, I mentioned this as well. So if you think about total development of at the one hand primary energy, but also world population, and we look into the fraction of the South in terms of percentage of energy, but also percentage of population, you can see that 1800, when we started out, we had roughly 10 exajoules of energy consumption in the world. New York has an energy consumption of 1 exajoule. So basically in 1800, the total energy use of the world was something like 10 New Yorks. So relatively small compared to today. Today, we are roughly at more than 500. But yes, this includes biomass. Yeah, this includes biomass. But what you can see here is also that basically 1 billion people in 1800 consumed 10 exajoule, 60% of that in the South, which is roughly approximated also by the population. So 70% of the 75% of the population have 60% of the energy use, which is a roughly equitable situation. Between 1800 and 1900, Industrial Revolution, energy use increases by a factor of 10. The share of South halves. Basically, the South is falling back because industrialization is happening in the North. 66% of the world population in the South, only 1/3 of energy uses in the South. We have a population growth of 600 million, so not even doubling, but an energy use of quadrupling. Sorry, factor 10 is here, of course, quadrupling. And then the further acceleration, almost exponential growth between 1800 and 2000 in terms of energy use up to the year 2000. We are already very close to today's energy use, and also the inequities remain extremely strong. 80% of the population live in the meantime in the South, and only 40% of the energy use is in the South. So basically the equity continues to persist. And if you look into future scenarios, and these are the ranges across the so-called shared socioeconomic pathways, you can see basically futures which are in terms of energy use quite equitable or less equitable. But one thing most of the scenarios have in common is that most of the population will also over the coming century be in the South. And most of the expectation is that the energy demand growth actually is slowing down compared to what we have seen historically in the last 100 years. Even though that there is a wide variation here, you can see that the highest scenarios are only a factor 4 growth. Actually, low scenarios keep energy use below today's levels in the long term, driven by a sustainability transition. Okay, so historical perspective, let me conclude perhaps with some observation about fossil fuel reserves and resources. Very often you hear in the literature that we are running out of oil. I think it's really important to keep, that's actually me. Where is it? Sorry, Ottmar. Okay. Okay, so Yeah, so I just turned it off. Yeah, so very often you hear that we might be running out of oil. I think it's not so prevalent anymore nowadays because the discussion shifted to we need to reduce oil anyway, whether we run out of it or not. But I think it's really important to keep in mind that if you look into proven oil reserves over time, 1998, 2008, 2018, this is from BP statistics, BP Amoco statistics, which bring out basically a state of the current understanding of how big the reserves are. The reserves have actually been increasing over time. The reserves is the amount of oil which is extractable with today's technologies as today's costs. And these reserves have always been increasing. They have not been declining because of extraction. And one of the reasons is that basically technological innovation. We have improved our technologies and can basically extract more oil from the same places than we could in the past. And therefore, the reserves have been increasing. It's only part of it that we also discover new oil, but our technologies have improved in the past. And this is also the reason why we are not running out of oil. But if you look to an important factor here is the R2P ratio. That's the reserve to production ratio. Basically, if you think about reserve at a certain point in time, compared to the annual production at that time, how many years do reserves last in the future? Over the past 50 years, this has always been around 50 years. So no matter how regional R2P ratios actually changed, and even though we had some new reserves in Latin America particularly, the R2P ratio of the world was relatively constant. So this perception that perhaps we are lucky and we run out of fossil fuels early enough is a very unlikely scenarios given the realities on the ground. Some of the very important recent innovation in the fossil area was the shale gas and the shale oil revolution, which changed basically reserves, particularly in North America. And I think it's important to understand how quickly those changes can happen. What you can see here is basically technology innovations on different scales that basically determined the success from shale gas in the US. So what happened here between 2007 and 2011 was basically that the industry learned to drill very quickly basically the exploitation time decreased, while at the same time the horizontal drilling capacity of the industry decreased very rapidly. Whether you can extract shale gas economically from the ground depends on how far you can drill horizontally. What you do is you put a chemical underground, you crack the gas formation, and then you suck out the oil. And the better you can, of course, drill to where the gas is, the more oil you can extract, the more economic it gets. And within a few years, the American oil industry basically managed to double the lateral lengths, the radius of the drilling, at the same time reduce the drilling days that it needs, kept the costs constant, and increased, of course, because of the lower costs, also the production capacity, and has become a major gas exporter. And if you think about the recent responses of Europe to Ukraine, it has been to basically go into big contracts with the US. So in the future, we will also have shale gas in Europe. This is technologically a success story. It's environmentally not a success story because there are many environmental problems that are created by shale gas extraction, and many deal with, for example, pollution of water because of the chemicals that are put there, and agricultural areas have been compromised, and also drinking water in the US have been compromised in those areas where there is a lot of shale gas drilling. But in principle, what happens here is, and this is not only the case for fossil reserves and resources is that you can think about the available resources underground as a resource triangle. On the bottom are basically the difficult to extract formations. We have gigantic amounts of gas hydrates, for example, in the Earth's crust. And up here are those that we can extract with current technology. And the higher the prices are, the more you go into those difficult to extract grades. And the better the technology is, the more you can go down here. And what happened basically over the recent years was that shale gas was bumped up from the bottom of this pyramid to innovation to the top of this pyramid. And that's happening all the times. And that's not only happening in fossil resources, that happens also for minerals. So if you think about minerals, copper, iron, aluminum, or lead in the past, in 1950, we thought that we had this amount of reserves for these different minerals. Look at copper. Copper, the estimates of the geological surveys was that we had something around 100 million tons, or is it billion tons? I should have written down the unit here. But in 1950 to 1980, basically we produced more copper than we thought would be available in 1950. Yeah, and in 1980, the estimates of future reserves was about 500, so 5 times bigger than in 1950. The same, almost 5 times bigger in terms of iron, aluminium, and also lots bigger in terms of lead. So what we, 2 hands, let's start in the back.
These materials, can you produce them in a lab, or it's like oil that when it's over, it's simply over?
You produce them, you mine them. So you have a copper mine, and then you mine them like fossil fuels. So you do that, you don't produce them in the lab. I would not produce iron. Aluminium, you can actually produce also out of scrap. So some of it can be recycled, but generally you need to mine, you need to mine those materials.
100%. So steel and aluminum from recycling perspective can 100% be recycled, and almost 90% less energy is used if you use recycled aluminum, and same goes for the steel. And steel, I think they say that's 4 lifetimes or something like that you could use steel and stuff. So, but yeah, for iron production, it's a different story depending on how you produce the pig iron versus sponge iron.
Thank you. Thank you, Sarita.
It's just a quick question. Do you know the, yeah, it's nothing. Do you know the 2020 values of the reserves? Or has it increased, continued to increase?
Actually, unfortunately, the geological survey stopped to do this long-term reserve estimates, which is a real pity. It's a real pity.
Yeah.
Yeah, but I think not of all of them, at least. I think copper exists, but I think lead, aluminum, iron does not exist in the same regular scrutiny that we had in the past. It's a pity.
I suppose that science has an idea of if the trend continues or if it's.
I think this is something that we do now in our models, right? Where we think about what are future requirements. And I think we can learn from this type of historical perspectives that if we plug into our models the current reserves and availabilities, perhaps with an underestimate.
Yeah.
Probably with innovation, you will get actually larger amounts into the future. And we should vary those amounts when we do the analysis. Yeah, but it's a good question. Yeah.
Reserves here is just everything that is already exploited. Not something we know it's there, but it's not touched because it's too expensive.
So reserves, so there are resources and there are reserves. For reserves, there is a very high likelihood that they are there. They are usually proven not necessarily by having drilled but by basically how do you call that? I forgot how this is called, but you basically can look on the ground and then you find it digitally, but you are relatively sure that they are there. So there's very high certainty that they're there. And there's also very high certainty that at current prices and technologies, you can extract them. The resource base is again, at least an order of magnitude bigger than those. Yeah. So that's why technology is important, because you have this huge resource base. You can extract a small fraction of reserves out of them, and technological change always manage to basically convert resources into reserves, and that's the reserves here.
Maybe one small thing to add is that we do this partly by technology development, and therefore we can actually have copper at lower ore grades being available. But it's for copper, as well as expanding reserves, we see also the falling ore grades, which means more and more energy use for the same amount of copper that we mine.
Absolutely, absolutely. So this is also the same with fossil fuel extraction. We have learned to extract more and more with new technologies, but all of that new extraction is actually environmentally more degrading, and it's also more energy intensive. So we need some energy to extract energy, which is of course a problem. The same for the mineral reserves. Thanks, Detlef. Yeah, and then perhaps I should move actually to the future, but let me perhaps make some other observations. How quickly technologies diffuse into the market depend a lot on the infrastructure needs, and it depends also whether you are in the center of the innovation, the frontier, or whether you are a country which actually is adopting a technology where a lot of experience has been gained at the frontier. So whether you are a lagger or you are basically a late adopter. And this is a very interesting figure here. It shows you basically the diffusion of railways in Europe. The center, of course, in the UK, and then how in Central Europe basically trains emerged first, and how it took more or less half a century until the trains were also applied in Russia and further away. So that's a typical slow diffusion of technology, which takes decades because of the big infrastructure needs to change the system. And one thing that we have also learned about spatial diffusion characteristics of the past is that basically we have the distance to the innovation center. So the later you basically adopt a certain technology, the later you adopt it and the further you are away from it, actually your adoption time is slower when you're further away. So if you're a latecomer, you can adopt the technologies more quickly than the first one, but your adoption intensity or dense is also much lower. So usually the first adopter completely adopts the technology and replaces it into the market. The late adopter does it more quickly, but not so comprehensively. Yeah, because already the next technology comes in. And this is that those diffusions can happen relatively quickly. I wanted to give you an example of the car. The car diffused very quickly into the markets, much more quicker than the trains, because they are less infrastructure dependent. So here, and how quickly this can happen is, I think, shown nicely by this picture. This is the Easter Parade in the Fifth Avenue, New York, 1900, horse carriages. This is 1913, 13 years ago, only cars. Is it only cars? No, you can see actually, can you see the car? The car is here. There's one car in this picture. And can you see the carriage here? There's also a carriage here. So, but the main reason of this picture is to show you that this happened in more or less in less than 2 decades. Trains required half a century to really diffuse. So a good example why demand side transitions are so important. Actually, moving away from cars, from horses to cars, had also some big environmental benefits. Generally, these changes happen because you move to a new mode, which gives you a better service, and cars provided a better service compared to horses. They are quicker, you can transport easily more people with them, but very often those changes are also associated with environmental improvements, and there were huge environmental improvements when we moved from horses to cars. And the main environmental improvement was, of course, the manure of horses in cities. Cities smelled differently before cars were in cities, yeah. And they were even louder. Horses were louder. I would doubt that. but generally, this transition here led to enormous increase of efficiency. So this is a typical car in the 1920s, a typical car in the 1990s. Animals and also humans are actually not efficient machines. We had solid waste, and we just talked about this, but also basically carbon emissions, per kilometer drops if you move from horses to cars, simply because you have to feed horses. And the emissions of horses in terms of carbon equivalent are quite high. So we have some autonomous improvements, even in cases where we would not expect to have them. Excuse me? Yeah. Exactly. It's an excellent observation. So these autonomous improvements that we had in our system, these improvements in efficiency, improvements in technology, were too slow to compensate for the massive increase of the system itself. Yeah, so we drive much more kilometers nowadays than we drove earlier. And that's why overall, of course, cars create much more CO2 emissions than horses ever did. But per kilometer, and if you think about a horse here and the car there, the horse is unfortunately also environmentally less friendly than the car. Yeah, so many things have been enabled by the fossil system as we know it now. A lot of welfare has been created. Without fossil fuels, cities would not be possible. We have added a lot of convenience to our system, but we have created also many different problems. Yeah, so the current system is very inequitable. So we have energy poverty in the world. Many people do not have access to clean cooking or heating fuels. That's a major mortality. So this is actually the major killer of the energy system, is that people do not have access to the right form of energy, so electricity or clean cooking. We have increasing trade-offs with land, where we basically have large amounts of bioenergy, and there's potential conflicts with food. The energy system is causing air pollution. We increase water stress, either to thermal power plants, which basically creates, because of cooling, thermal pollution to the rivers, but also you need to withdraw water for cooling. And of course, perhaps the biggest problem of the current system is greenhouse gases and climate change. And you have heard a lot about this. But these are multiple problems that need to be solved at the same time. And in order to solve those issues, and particularly in order to achieve to limit warming to 1.5 degrees, and now I'm moving from the history to the future. And I think you have heard most of this already, but basically, in order to achieve 1.5 degrees, which is perceived as the defense line where basically dangerous anthropogenic climate change starts to happen. We need to have a very rapid and immediate emission reduction in all sectors. We need to achieve net zero emissions from the energy system by 2050, for which we have a range of different technologies available, and different choices may lead to different pathways. Behavioral change can help us a lot. So changing lifestyles without necessarily sacrificing can help us to achieve these goals even more rapidly. In all of these cases, we need to massively increase investments into the low carbon options, particularly into infrastructure. Two good news here when we talk about achieving net zero emissions by 2050. First of all, achieving net zero or carbon neutrality does not mean that we have to basically shut down or reduce emissions of all activity to net zero. So net zero energy system will be a system where we have some residual emissions in some sectors where it's more difficult to abate, which need to be balanced and compensated by increasing sinks in other sectors. And this sink can be either to conventional measures like increasing afforestation, but it can also be by, for example, combining bioenergy use and creating electricity and heat, and by combination with carbon capture to basically create an anthropogenic sink, producing energy to bioenergy, while at the same time basically removing CO2 from the atmosphere and put it underground. Are there any other ways that we could reduce CO2 from the atmosphere other than forests and bioenergy plus CCS BECCS? Have you had any, did anybody talk about this earlier? What do you think? Would this be the only options that we have? Excuse me? Less. Well, wait a second, but every person that breathes takes CO2 out of the atmosphere, not permanently. So less population probably is good mitigation, but not CO2. So what options do we have to remove CO2 from the atmosphere? This is geoengineering. We just talked about it when we moved. Yeah, please.
I think Europe now is having some geoengineering to repeat. So I think Europe now they are doing some with the European Commission. They didn't set the policies yet, but they are working on things like that. But they are wondering if it's gonna impact and do more differences between Europe and other countries. So.
Do we really take CO2 out of the atmosphere if we do solar radiation management, if we increase the reflectivity of the atmosphere?
Don't let the warming.
Yeah. So there are proposals that you have a solar shield somewhere, or that you basically spray CO2, spray sulfur into the stratosphere, and then sulfur builds small aerosols, which means each particle is then coated by water vapor and water like a cloud, and that of course would then reflect more. So these are proposals which are out there. It's of course another planetary experiment. Yeah, so I'm not sure. So basically you exchange greenhouse gases in the atmosphere with sulfur in the stratosphere. I'm not so excited about it, but what other options do we have to take? Yes, please.
Like or biochar or direct air capture, iron fertilization, wave pumps. There's lots of crazy proposals.
Super. Yeah, exactly.
And more. Yeah.
Exactly.
But
exactly. So basically, you can try to get the CO2 into all other places than the atmosphere. You can try to push it into the ocean by making the ocean more fertile. You can, as you said, you can directly take CO2 out of the atmosphere. DAC, it's called, but nothing to do. It's not for eating. It's AC. Yes, please. Enhanced weathering. Yeah, basically you take basalt, a stone, and then you gravel it, and then you put it. You disperse it everywhere, and then you hope that mineralization happens before somebody is putting it underground, because then it doesn't happen. But this is also an option which has been proposed. Yeah, indeed.
It's a bit of cheating, but ChatGPT suggests direct air capture, which is technologies involved removing CO2 directly from the atmosphere.
Yeah, this is no. Who said that? You said it. Yeah, you said it. You said it. Yeah. Thanks for confirming it. So 2, and then we continue. Then Sarita, and then
I mean,
Sophie.
here something which is not considered yet is the blue carbon sequestration, because the research on that, I mean, there is a lot of literature, but it is not being considered in AFLU. And maybe if it is considered, because some of the study says that compared to the LULUCF, the forestry sink, the blue carbon sink is much more higher. And this is apart from the carbon sequestration, like directly into the sea.
Yeah.
So that could be added into the.
Yeah. Valentina, I cannot say no.
Dr. Bauer and Dr. Drouet, after large amounts of beer, suggested, no, Dr. Drouet didn't have beer, suggested that we should build a tube and then send it to the atmosphere, outside the atmosphere, sorry. But I don't know how we don't know how that's going to work, but they were suggesting this new method. I'm sure ChatGPT doesn't know that.
Yeah. Yeah. But I like to solve climate problems without sacrifice. So did you say putting beer into the atmosphere? Tube. I thought you would put CO2 into beer and then you shoot it. Sophie.
Actually, yeah, using the CO2 in the industrial sector or construction sector. So using it in products and keeping it there. So hopefully.
Very
for
good.
long
Yeah.
term.
Yeah. So this is actually an option which is not modeled so well at the moment in many of the integrated assessment models, but gets a lot of traction in Europe. So there is this Bauhaus initiative, which basically is talking about over centuries converting the biospheric sink into an anthropogenic thing. So, and you can do it in products, you can do it in houses and so on. Yes. Yeah, super. We come back to it actually. There's a list of CDR, carbon dioxide removal options that I want to come back to. But coming back to this picture here. Basically, you have some sources, some sectors that act as sources, some sectors where you remove CO2 out of the atmosphere. On balance, you need to achieve net zero CO2 emissions between 2050 and 2070. And the EU has a net target of net zero GHGs by 2050, which basically means net zero CO2 before that, something around 2040, 2045. The EU wants to achieve net zero CO2 and net zero GHGs. The models at the moment tell us that this sink here, and these are different modeling frameworks. This is, for example, the Italian model, the WITCH model. This is our model here at the ASA. This is Remind Magpie. This is the PIC model, Nico's model. Image, Detlef is here. No, he was here. So that's a Brazilian model of Roberto and colleagues. This is the Japanese model. And all of them give you basically a different estimate about how much negative emissions we need in order to, or how much actually these residual emissions are that you need to offset these negative emissions. And the estimates are between 5 to 10 gigatons. Roughly, these models suggest that you need to offset the residual emissions. And what we model at the moment is mainly biomass plus CCS and afforestation. Most of the other things are not included. I mean, the WITCH model was the first to include a DAC, for example, direct air capture, which we talked about. Some models have included biochar in the meantime, enhanced weathering, but there is a lot, I think, still to do until we have a similar good understanding of the whole portfolio of negative emissions technologies. Is 5 to 10 gigatons a lot?
Per year.
Per year?
Yes.
In 2050? Yes. Yeah, so it's all 10 gigatons is always a quarter of today's emission. So basically you have a future system which takes 25% of all the emissions that we today emit into the atmosphere out of the atmosphere. That's actually very, very big activity. Very big activity. Nico?
One comment, depends on how much it costs.
So how much does it cost to get the CO2 out of the atmosphere? I mean, if you get it cheaply, then it's probably not so much a matter how large the mass really is. But my question rather is, what year is this bar chart? 2050 or 2100?
No, this is the time when the models achieve net zero. So this is a different time for each model.
Okay.
But if you basically go to net zero, at the point of net zero, you have a certain balance.
But this is then around 2050, 2060.
Between 2050 and 2070.
So it's a fast ramp up also. That's
yeah, it's a fast ramp up. Yeah. Sarita?
I wanted to check about the uncertainties for each of the technologies. So basically an uncertainty of a carbon sink through natural resources like Afalu versus technology, man-made technology like DAC, or is that considered, or is?
I don't know. Tell me. But no, so I would say not sufficiently. I would say not sufficiently. So what is in there, I think, is some differing representation of, for example, the costs, some different representation of the forest sector and how quickly you can do afforestation. The models differ a lot here. What is not in there is actually some of the risks that we know exist. Yeah, so we see already now that we have lots of pests and diseases in the existing forest stock, which makes very difficult to retain the current CO2 removal by the biosphere, by the anthropogenic biosphere. If we have further climate change, the likelihood that actually some of those forests will turn into emissions is relatively high. This is not included in here. Yeah, so I would say there's actually quite an optimistic estimate of how much is there. And another thing that is not so well integrated in our tools is that if you actually get to, if you manage to take CO2 out of the atmosphere and your CO2 concentrations start to fall, your CO2 fertilization effect is actually gone, right? CO2 fertilization means that the higher the concentrations in the atmosphere, CO2 concentration, the more quickly plants grow. Then you start to take CO2 out of the atmosphere, CO2 concentrations decline, and some of the forests simply will start to emit because they will grow slower than they will have the same decay, but they will grow slower. So they will start to emit, and I would say that that's also not very well represented. It is represented, but not very well represented in our models. So we are somehow quite optimistic in what can be achieved. Yeah, these differences. How much time do I have?
35 minutes
Left?
40 minutes.
Okay, we will go to a fraction of my presentation today, but yeah. So basically, what this means is, by around 2050, 2070, these sectors which are negative here, they need actually to be net zero much earlier than those sectors where it's more difficult to abate. So in most of our future scenarios, the energy sector and the forest sector is going to be net zero 10, 20, 30 years before the total system is at net zero, which means that industry sector, transport sector, building sector is at net zero a little bit later. And there are decades before that, our forest sector and our energy sector needs to be completely decarbonized and needs to become a sink. And this is not, for most of the policymakers, is actually not so clear at the moment. Most of the policies that at the moment generated is if you have a 2050 net zero target, the reflex is every sector has to be net zero by 2050. That's actually not what the scientific literature says. And I think it's important. The y-axis here is frequency. This is the time. Yeah, let me explain. Perhaps I should explain it more clearly. So this is the time where we globally achieve net zero with the full system. These are years earlier than the global system. These are years later than the global system. Energy supply sector is, and this is a distribution of all the model runs. Yeah, so most of the model runs achieve energy supply sector net zero 10 years before the total system, but there are also models which achieve it 40 years earlier. Yeah. And the AFALU sector actually becomes net zero already 2030-ish, 2030, 2040. It's the easiest. You just stop deforestation and AFALU becomes a thing. You don't even need to afforest for that. Just. Yeah, it's not so.
Are they all the same, all 1.5 degree runs?
These are all the 1.5 degree runs. So some of them are image runs, some of them are message runs, but they are from the Engage project. So that's a nice thing. So they are actually from the project which is organizing our summer school. And that was a paper which generated 600 scenarios in the IPCC database. So most of the scenarios in the IPCC database come actually from this project and from this exercise. Yeah, so if you think about future transformations, and basically you find in the literature mainly two different perspectives of how to get to net zero. Basically, there is the perspective, and I would call it the conventional perspective, to get to keep warming below 1.5 degrees, where you basically emphasize a lot supply side options, which scale slowly and need massive long-term deployment under relatively high demand, which creates a certain overshoot and is associated with inertia in policies. And because of that overshoot of the 1.5 degrees, you need to take later CO2 out of the atmosphere. And the higher this overshoot is, the more in the long term, basically you rely on negative emission technologies, which are controversial and which basically also not really proven on large scale outside the forest sector. Another perspective to achieve 1.5 degrees would be to try to accelerate transitions through demand side solutions and a bigger emphasis on granular small scale technologies. We know from empirical studies that small scale technologies and transformations which are driven by end use change, innovation, but also behavior basically can accelerate the energy transition. And because of that acceleration and combined with granular distributed supply side options, we can keep the overshoot low. And if we are able to keep the overshoot low, we do not rely on massive deployment of large scale negative emissions in the long term. So one of the key issues is try to understand how can we actually accelerate the system? How can we initiate this demand side transition? And why is it important also to focus on the demand side? This is also because if we think about the energy ladder or the energy efficiency ladder, let's focus up here on total energy. Then most of the losses that we always see are happening at the demand side. The point of use in the appliances, how we use the appliances, we destroy most of the energy. We waste most of the energy there. So a demand side focus will help us also to enormously increase the efficiency of the system. How can you interpret this graphic here? So basically you have here the total energy system, you have here primary energy, which is extracted, then you have some losses you get to secondary energy. That's basically the power plants. Then you bring your energy to the point of use, distribution grids, and to the at the useful point of where basically energy is used. And then you have cars, light bulbs, stoves, which basically transform your useful energy into services. And if you look into the fraction of energy that is lost, these losses dominate basically our energy system losses. Not in absolute term, but in the fraction of the share of the energy that we use at the end use level. So focusing on this part also will reduce the whole need for the chain as well. And this is something that we can see in different services, but we can also see it beyond energy in materials production, for example, as well as when we think about water use, irrigation for providing the crops. So it's also where most of the efficiency losses are happening at the moment. And in order to transition to basically a service-dominated demand side system, it is important not only to think about technological transitions, but also about social transitions. And there are a few trends which are already ongoing, which might support us in this demand side transition and might help us to keep demands low. And these are, I would say, the five main transitions that are ongoing and which we are participating in. On the one hand, we have changing consumer preferences. So we are moving more and more to vegetarian diets, which is, I think, very visible in particularly our Western economies. We have a generational change in materialism. I would say also supported by the digitalization. The focus nowadays is much more on the quality of the service than really owning that service. So it's not so important whether you have the car yourself, but you want to get from A to B in a convenient and quick way. I think that's very different to my generation. For my generation, at the age of 18, we all wanted to have a car. Car was very important. It's a symbol of freedom, it's status, etc. And this is, I would argue, it's coming down. Yeah. So I don't dare now to ask the question, who has a car? don't be. I have a car, but don't be. It doesn't. If you have a car, it doesn't mean that necessarily it has been your objective to have a car. Nowadays, very often you have to have a car to get conveniently from A to B. We don't have this alternative system functioning yet. But I would argue that for most of you, probably the car is not the main objective, right? So it's the mobility which is the main objective.
It's a status that's the main objective.
The status is the main objective. So see, for Kai, the status is the main objective. It's a generational thing. Yeah, but exactly. So we focus more on service, I would say, than ownership, and digitalization has helped. We see emergence of new business models. So the sharing has become much more pervasive than it used to be. We have circularity, of course, not even close to what we can achieve, but I would say it is in the minds and in the policies. And the biggest ally here is digitalization and the so-called ICT convergence. So basically, we have many new devices and tools which bring multiple services together. So if you think a mobile phone is not only there to call somebody. Mobile phone can mean access to bank, where you don't have to drive to a bank. A mobile phone can mean a new mobility services. So you use the mobile for many other things than just calling, and that also reduces. It is ICT convergence, and it reduces the need for energy. And then, of course, granular technologies that are connected to digital services are critically important. Some examples for really rapid transitions. So this is basically in the last 13 years, consumption of meat substitutes worldwide, an enormous and these are million tons. It's an enormous exponential curve, which shows that there is increasing acceptance of those technologies. Or if you think about driver's license and ownership of young people. So even in the US, the fraction of young people who have a driver's license, particularly in urban area, has dropped massively, has dropped by 20 percentage points. That's a very big and very rapid change. But it's it's basically an urban rich phenomena at the moment. And we need to think about how to go beyond that area. Moving away from bulky, large-scale, lumpy technologies like the Airbus here or like chemical factories here, and relying more on small-scale technologies have four main benefits. So one is small-scale technology learns faster. Why does small-scale technology learn faster? Because for a specific, let's say for 1 gigawatt of capacity, if you rely on nuclear, you build the plant exactly once. So So you don't learn much if you build one nuclear power plant. But if you want to provide 1 gigawatt capacity to solar PV, you need to build 100,000 of cells. And you repeat this building a cell many times. And every time when you repeat it, you learn something. And that explains why small scale technologies learn more rapidly for the same output. It's the units that you build which determine how much learning you have, not the capacity. And therefore, small scale technology learns faster. Small scale technology diffuses faster into the market because often it's not related with and dependent on big capacity, and small scale technology is also less risky in terms of its investment. You cannot build a nuclear power plant without government support. Nobody will take the risk of that project. So you need to really think about a financial mechanism that is able to carry the risk of a huge project. And many developing countries do not have the governance or the security to do this. It's much easier to do 100,000 of small solar projects because the finance is less risky, is smaller. The risk can be divided among many, and therefore also it is basically a lower risk if you can build technology smaller and build it also more modular. And that's one of the reasons why the nuclear industry is thinking to build basically small scale modular power plants, because also it's not also then it could be useful for future nuclear innovation and also reduce the risk of nuclear technology. But all in all, if you think about examples of studies that have shown how moving from more large-scale technologies to more connected and granular technologies, what the benefits could be, many different studies exist on the city level. These are not the big integrated assessment models that we run, but for example, the International Transport Forum, the OECD has made dozens of studies of different cities. This is a example for the city of Dublin, where they show how shared mobility could look like in cities like this. And in most of the cities, or actually in all cities where they did the study, a very small fraction of the infrastructure and a very small fraction of the vehicles is actually sufficient if they are shared in an effective way to provide the same service even in a better way. So in Dublin, only 2% of the cars are needed if you have all the information available of where the demand is, where the mobility demand is, and if you would be able to distribute the cars among people and share them, only 2% of the cars are needed to provide the same service. And that 2% of cars would lead to many benefits. Basically, the kilometers driven could be reduced by almost 40%. Greenhouse gas emissions would be reduced by 31%, only of the driving, not thinking about 98% of cars that would not be produced. Yeah, that's not in this number. Congestion would be reduced. So basically, quality of life in cities would be increased. If you only have 2% of the cars, if you go on the street, there is almost no car left, right? So, and you would also basically free up space either for greening of the cities, or you could use the space for social interactions. Why is it acceptable to us that in a city we have only 1 meter to interact? The rest belongs to the car. It doesn't need to be like this. We just got used to it and we accept it. We accept that our streets are full of garbage, more or less, because they are not used, the cars. 90% of the time the cars are standing there. If you would have an open mind and if you would think about how to best share the infrastructure, instead of everybody owning an infrastructure, we would only need a small fraction of current cars, and you can show that in models. Basically, there are many different disruptive end user innovations possible. This is a figure by Charlie Wilson showing basically how at the household level, at the mobility level, at the appliance level, one could basically move away from the old-fashioned ownership model to a more usership model. share appliances and build a network of smart and intelligent end-use appliances, and to that also create a new system where the service is better, but at the same time energy use is reduced, similarly to the example that I showed earlier in the mobility example. What is the main barrier for something like this? Is that it sounds like something that we should all do, right? So basically, you would have a better infrastructure, you would have a better service. It doesn't cost anything. It has social and environmental benefits. So why are we not doing this?
People don't want to change.
People don't want to change. Yeah. Really, people don't want to have better service at lower cost? No. Path dependencies, yes. Path dependency. One of the main reasons is, of course, that these benefits can only be realized once you have this alternative system also functioning and working. Yeah, so you need to establish it in parallel to basically removing a quite sophisticated and functioning system as well. So without having it as an alternative, it won't work. And many of these digital services require that we also are able to share data openly among ourselves. Yeah, so we need a complete reform of digital data usership and ownership. Without that, it will be very difficult to implement things like this. Actually, the Netherlands is a very good example how some of these things work quite nicely. So if you go to, we talked about Groningen and other cities where you have a very nice spirit of sharing and a lot of bicycles, but this is also because the whole infrastructure is developed around it. Yeah. So without that infrastructure, it is not going to happen either. Yeah, but I'm very, so basically the main point that I wanted to make here is that it is laudable and good if you think about conversion efficiency of individual appliances, but at the end, we have to think about new ways of providing services, of new devices that are able to basically integrate many different services at the same time. And if you move, for example, if you think about, for example, the mobile phone has replaced a number of different devices. It has not only reduced the basically the energy consumption for those services, it has also massively reduced embodied energy. So basically producing a mobile phone is of course much less energy intensive than producing all those other devices. What we have to learn is how we can replace all those other devices by the mobile phone and don't use the mobile phone as the remote control of those other devices, which we see happening at the moment also sometimes. Sometimes you have the mobile device in addition to all these other devices as well. Yeah, not always. The mobile phone in many countries has replaced banks. So many banks are going back because people are doing digitally the bank services, for example. But for many other things, I would argue they're happening in parallel. Should we make a quick break?
20 minutes.
20 minutes left? Okay, then let's go through. I'm just getting okay. So this means also, and that's consistent with the same demand side scenario, that basically a major demand side focused transition would also create rapid electrification, and at the same time we have rapid diffusion of renewable energy. And if we so it will not be enough to only change the demand side system. If we have a very distributed renewable based system, we need to think about two things in addition as well. So we need innovation in, at the one hand, the grid. So we need to be able to create a better grid, but we need also to think about how can we store energy in order to overcome the intermittency of renewables. And the intermittency of renewables is not only there between day, right? In the night, there is no solar. The bigger problem actually compared to the daily fluctuation is the long-term storage. What do we do seasonally? Because renewables produce less energy in winters than in summers. We need to store energy in order to be able to do that. And we need to have the right type of storage so that we can compensate in a very quick way the daily fluctuations, but also store energy with low losses at low cost for long term. And there are many unconventional options that we could look into and which require more research. And some of them I'm showing here. So everybody, I think, knows pumped hydro. That's also something that we have in our models and can be used for seasonal storage. But of course, pumped hydro is something for which you need a mountain close by. And it's not available everywhere. And the potential is also not large enough if you think about the full renewable system, for example, in Europe. So we need to think about other things. Therefore, there have been many different suggestions to use the oceans as energy storage possibilities. So there are, for example, suggestions to take Beyoncé energy storage. So instead of go to a turbine, you could press objects under the water when you have of energy and then let them come up again and produce door basically to the upwelling force of water energy. And first power plants, Beyoncé power plants have also been so the first pilot project are also running at the moment too. And this is important because if you don't have mountains, sometimes you have a coast. So you have your coastal area is you don't have pumped hydro, but you have the deep ocean to store energy. Another, sometimes perhaps a even more unconventional storage possibility is compressed air deeply underwater, or a hydrogen link, a deep ocean hydrogen link. This is interestingly, but this would mean big infrastructure projects, but would be very, very efficient and also cost-wise be relatively low cost and could also be used for seasonal and multi-year energy storage. There are many, many different proposals to use basically in water poor areas to use sand, for example, instead of water. So bring sand up and then let it basically anything that you can lift up can store energy because of its gravity. And the same concept could work, for example, in lifts. So we published at the EASA all of these different options. Actually, this one got really a lot of traction. And in New York, there are already 3 skyscrapers who are adapted to use the lifts as storage, as a response to the paper that we have written 4 or 5 years ago. Yeah.
But you can probably calculate what the total potential is. What are the projections of? Okay.
Yeah, go ahead.
Yeah, I think it's basically.
Yeah. So for these technologies, we made first estimates in terms of the potential. And the potentials are very, very different. Yeah. Beyoncé is almost infinite potential. However, you need quite deep oceans. For example, we have very little potential in Europe because the North Sea is too shallow for really big Beyoncé storage. Also almost infinite potential, but I will get to that. So for these options, we tried to, and this is the potential curve for mountain gravity for different regions in the world. You have for most of them relatively different storage potentials, obviously because of the topography, but also because of many other factors. And this is the storage potential, for example, of the Beyoncé technology. The potential is much, much bigger than the global electricity needs. Europe, unfortunately, not so well covered. There is storage potentials on the Spanish and on the French coast, but otherwise it's relatively low potential. And if you compare all those different technologies to each other, you can see that they differ, those different technologies, mountain gravity that I showed, electric trucks. So there are 2 different types of gravity storage systems, the lift system. Perhaps this is the reference system that you want to compare to. So this is the seasonal pumped hydro storage, the Beyoncé system, the deep hydrogen ocean link, and then the deep ocean compressed energy infrastructure. They all differ in terms of the installed cost, installed capacity costs, the energy storage cost. You can see here that basically seasonal pumped hydro is low compared to the electric truck or to the lift energy storage. Yeah, we're talking about orders of magnitudes difference, but we have also the deep ocean hydrogen link, which is actually not so much more expensive than the costs for the seasonal pumped hydro. Then they differ a lot in terms of the size, but they differ particularly in terms of the storage cycle. And I think that's really important. So lifts cannot be used more than for weekly storage. Yeah, lifts will not help you with the annual storage problem. There you need to look into gravity storage, into ocean storage, in addition, of course, to pumped hydro. And this gives you somehow an overview of how to bring all of these together. Here you have the energy storage capacity of different storage options. Here, basically, you have different energy storage cycles, daily, weekly, monthly, seasonal, and also multi-annual. And this figure shows you also why we are talking about hydrogen, ammonia, e-fuels, synthetic fuels, because they can actually cover the whole area here. They can be built extremely large, and they can also do any type of storage. So these are very, very flexible fuels. The lift and the batteries basically are only useful here. So we cannot use the current batteries to basically make our electricity system more reliable. If we really only want to do it with renewable energy and batteries, we have to curtail a lot of energy. We will be very, very inefficient. We have to go beyond that batteries. 15 minutes? 15 or 5? 15 minutes, okay. Okay. So I can go over this relatively quickly because these are all the different options in terms of removing carbon dioxide from the atmosphere. We discussed this earlier. This is actually a graph from the IPCC report. As you very nicely indicated, there's not only the possibility of afforestation, but there is on land actually also the possibility of biochar and soil carbon enhancement. Both are very promising options because they create a lot of co-benefits with other objectives. So if you use biochar, for example, which is using wood talking too much, pyrolysis. So if you use wood in pyrolysis, basically you burn wood under too little oxygen so that it becomes char. You can use that char in the soil. And when you use that char in the soil, you reduce the water need and the fertilizer need for the soil. So you reduce the farmers' vulnerabilities on the fluctuation of prices of fossil fuel fertilizer. That's a really interesting option for developing countries. So basically you would have an option that increases your agricultural productivity, reduces your dependency on fossil fuels, and at the same time, it can take CO2 out of the atmosphere. And it is small-scale technology. Yeah, so it's a granular technology that potentially can diffuse very quickly into the market. So very interesting biochar. Enhanced weathering has some of the same components, but with much more uncertainty. So some of these options are actually not so proven whether they can actually capture that much CO2 from the atmosphere as some of the enthusiasts think at the moment. So we need also to apply it more at scale. Then we have the ocean options, because all of them are about increasing the ocean uptake either to biological or to other methods. And you have the typical technology-based methods, which is direct air capture, biomass power plants, etc. There is a wide portfolio. All of them have different trade-offs and synergies. For all of them, the legal framing is not very clear. So we don't have international standards for that define permanence. We don't have international standards that clarify who is liable in case the project does not work. Yeah, so basically think about a forest where you get lots of certificates, then the forest burns down, CO2 is in the atmosphere, who is liable for it? Because the one who is liable would need to do the next forest project. Yeah. And we need to think also about policy portfolios that incentivize CO2 removal from the atmosphere. So with exception of biochar, which has some other advantages, these are technologies basically with which you take CO2 out of the atmosphere. The only benefit is the CO2 removal compared to other options that exist. So we need to think also a policy framework that would incentivize CDR and decouple it from the mitigation market so that you don't create also a competition between taking CO2 out of the atmosphere and mitigating at the same time. Okay, so let me move now a little bit to the whole issue of fairness, of how are costs different in different parts of the world. If you think about model results that, for example, we have also in the IPCC, what we can see here are regional costs to achieve either 2 degrees or 1.5 degrees in different regions of the world. This is a cost-effective approach. So these are all IPCC scenarios which try to achieve 1.5 degrees, where mitigation is happening there, where it is most cost-effective at the end. And then we look into the economic costs regionally and how do they differ. And you see here a few abbreviations, and these are the abbreviations of different regions. This is the average global costs of the C1 category of 1.5 degree consistent scenarios. So 1.5 degree with a slight overshoot. And ironically, actually the costs in terms of GDP losses in these scenarios are the lowest in Eastern Europe, North America, and Pacific OECD, which is basically Japan and Australia. So the rich countries have low costs around 1%, and the poorer countries, Middle East, reforming economies, Africa, have here costs which are some factors higher in terms of the economic losses compared to the rich countries. Do you have an idea why these differences are so big? What is making mitigation economically so much more expensive in this part of the figure than in this part? This is actually a figure by Celine. This is by Max. That section is from Celine in the IPCC report. So what? Yes. Excuse me? No, it's not the government support, but it's a good. I come to that later.
I think if we use these cost runs, then like basically it's cheaper to invest in developing economies. So like more effort is like the burden sharing is not just based on cost and not on other principles. So yeah, the relative share is higher in development.
Some of it, yeah, this is probably some of it, but so what has the Middle East and Russia in common? What is particularly important? What makes the Middle East different from most of the other regions? Fossil fuels. So regions who rely a lot on fossil fuel experts as a source for economic growth are of course hit the most. Yeah. So in Europe, we have a double dividend here. At the one hand, we decarbonize our system. At the other hand, we rely on energy production and the value chain and keeping it in Europe, for example. Yeah, that's why it is cheaper for Europe, because Europe does not export fossil fuels and does not lose a whole economic branch. And this makes it also very difficult in international negotiations, of course, because the interests of different regions are very, very different. And we have to think about how can we help those who will be affected most by this transition. We have to make it also acceptable to those. So it needs to be also a system that creates minimum losers. Yes, Nico, was it?
I only wanted to add to the reforming economies in MEA countries also have very bad energy and carbon intensities. And when you tax CO2 emissions, the GDP reductions, the metric on the y-axis is reduced the most in these countries for internal reasons. It is not only the export of the fossil fuels, also because they have the very bad or huge dependency on their own fossil fuel reserves.
Yeah, so this is the argument,
exactly.
the argument that we had before. So we have both. These are very inefficient systems. That's why you do more mitigation there, because the mitigation generally is cheaper. But the main reason why there is a factor 6 different in the costs is not that. Yeah, and revisit the assumptions. Yeah. So this begs, of course, the question: is it feasible to achieve those climate goals? And now I've been so slow that I don't get to the main part of my presentation. 10 minutes left. 5 minutes. Okay, 5 minutes. Very quickly. So we're not going to talk about fairness. We don't just talk about feasibility, and I try to go to that very quickly. So you can, so very often if you talk with people and you talk, let's say, at home, or if you listen to TV discussions, people say this is absolutely not feasible. This is all this is probably will not manage to achieve the climate goals. And if people say that, they have a certain mental model and they make certain assumptions why certain things are not feasible. What we can do is we can also try to scientifically study what determines the feasibility of a certain pathway. And that has been the focus of research in our community recently. So it's important to ask yourself, what do we mean with feasibility? And the feasibility definitions that we took in the IPCC report in the last one is that when we talk about feasibility, we talk particularly about the plausibility of the underlying transformation given a certain temporal and geographical context. It means that feasibility might look different in the Middle East than here, and feasibility might look different today than in 20 years from now, where we might have additional, for example, technological options available. And we need to also distinguish about what do we evaluate. Do we evaluate the feasibility of bringing a certain option into the market, let's say upscaling of solar PV, or do we assess the feasibility of systemic changes, where we need to think about what is driving this transformation and what are the main levels of change that you can evaluate in terms of their feasibility. There's a increasingly rich literature about this. I want perhaps to focus a little bit on work that IASA and CMCC did together, and which also has been used for the evaluation of the IPCC pathways in terms of feasibility, and which basically says that if you look at feasibility, there is not only one dimension. There are multiple dimensions which at the end determine whether a certain future transformation has a certain risks to become infeasible. So first of all, feasibility is not a binary concept that you say, okay, 100 gigawatts of solar, is this feasible or not? There might be given empirical understanding of technological diffusion that there are certain risks that certain things might be outside of what is, for example, plausible. And the different dimensions of feasibility that we looked into are particularly geophysical feasibility, basically looking into whether what we see in the scenarios are consistent, for example, in terms of potentials for wind and solar, which can theoretically be achieved? Are things economically feasible? If you think about GDP losses or acceptance of carbon prices, stranded assets that you might generate, or the amounts of investments that are needed. Is it feasible technologically? Yeah. Do you rely on rapid upscaling of options that are perhaps not available in the market or not? Is it socio-culturally feasible? So many of the energy demand changes that we just discussed require a certain lifestyle change, require that we change some of our values, how we basically perceive a car, and that can also be a feasibility concern. And very important, of course, do we have the capacity to mitigate? And that's very different parts of the world. So do we have the institutions? Do we have the governance effectiveness so that we can basically mitigate emissions, if you think particularly in the IPCC context, in the developing country context? You can go quite systematically about it if you want to assess the feasibility of different pathways. What you generally do is, as step one, you look for each of the different feasibility dimensions that I just mentioned and try to identify indicators that describe these dimensions and that are also represented by the integrated assessment, by pathways, transformation pathways. So once you have an indicator which is relevant for a certain dimension, let's say for the technological dimension, the speed of upscaling of solar might be a feasibility concern. And so gigawatts per decade solar installations could be the indicator. And then next you need to think about thresholds from existing empirical literature to find, okay, what is the threshold for the upscaling of solar PV where it really becomes unrealistic? Yeah, so you cannot build an infinite amount of solar PV cells within a specific time, and you can use those thresholds to evaluate what you see in different scenarios, and you can have indicators across these different dimensions, and then we develop thresholds which basically at different stages and say, okay, there are low feasibility concerns, thresholds for medium feasibility concerns, and then thresholds where the feasibility concern becomes quite high. And then because we have many indicators and many feasibility dimensions, one has to think about how to aggregate that information into a certain feasibility score for each individual pathway. And once you have done that, you can basically say, okay, this is pathway, this is a demand side pathway, this has a feasibility score along different dimensions, which looks like this, and can compare that then with the feasibility risk of a supply side pathway, for example. Yeah, so we can look into a trade-offs, feasibility trade-offs across different dimensions. So I won't go to this now because we don't have the time really, but what you get then at the end is basically an evaluation of individual pathways, and these are two summary figures of all the IPCC scenarios that are consistent with 1.5 degrees and 2 degrees. Down here, you can see basically the distribution of the scenarios in terms of their geophysical risks, technological risk, economic risks, sociocultural and institutional risks. Red means high risk or unprecedented. Yellow means consistent with best case practice observed in the past. And blue means plausible, so no feasibility risk at all. And if you look into this, you can see immediately that the institutional risk sticks out. So in our IPCC pathways, we rely a lot on emissions mitigation happening in countries which are relatively weak in terms of their geophysical, in terms of the institutional and governance capacity. And that has been identified as a concern. And this is also why a lot of the integrated assessment modelers and modeling teams are focusing at the moment to get a better representation of governance and institutions into the models so that we understand mechanisms of how to overcome those weaknesses. Yeah. What you can learn also from this is how feasibility concerns basically change over time. So this is a time axis. This is basically the feasibility concerns, the feasibility score of the pathways. And we can see here quite nicely that in order to achieve 2 degrees or 1.5 degrees, all of them do one thing: the feasibility concerns go up. So just now, the feasibility between now and 2030 and 2040, feasibility concerns are very high, because that's where we need to change the system. Yeah, so we need to change the system now. And then once the system is changed, the feasibility concerns go down again. The more rapid the transition is, the larger the peak is. And one thing that we had learned also from the IPCC analysis is, if we delay mitigation, generally these feasibility risks are higher than if we act actually right away for the same target. Okay, so I'm 2/3 through, but I'm true to all my time, right?
Yes.
Yes. Yes. I'm on an overshoot trajectory, but unfortunately I cannot take out time. So
Thanks. No, but yeah, I think it's a good finishing the topic with the feasibility assessment. So yeah, thanks a lot, Kevin, first of all. I think it was a very